Do you guys have any questions from homeworks? I think we had like up through 15 was due on Sunday. Does anybody have anything they want to ask about before we dive into the news? Bella? You can do that, but you don't need to. So let me explain real quick the way you could certainly look at the picture would be totally fine. But you don't need to. So let me just show you how you can get away with not. So we saw for polynomials, there were like 4 basic shapes for the end behavior. Those are the 4 basic shapes, right? So by just looking at the degree and the leading coefficient, I can tell which shape my polynomial is going to have. And then from that, I can just write my end behavior using limits. So for example, if I looked at number 8, leading coefficient is positive and the degree is even. So it's going to look like this. So I'd say the limit as x approaches negative infinity of k of x is equal to positive infinity. And the limit as x approaches positive infinity of k of x is positive infinity. But you do not need to do it that way. You could certainly just look at the picture on your calculator, which would be fine. Yeah, so this using degree and leading coefficient is certainly effective also. Sure, no problem. What else? Okay, then. Let's begin. So we're going to start today by getting in our time machine. And we're going to go back to like 6th grade. I know, I'm not crazy about going back to then either. But we, in like 6th grade, we might have had problems like this, right? How would have you done this back in 6th grade? You would have done long division, right? You'd have done, okay, I'm going to put 23 out here. The 139 goes over there. Just as a piece of vocabulary, that number is the dividend, and this number is the divisor. And you go, okay, well, how many times does 23 go into 1? Well, 0. How many times does 23 go into 13? Well, 0. How many times does 23 go into 139? Well, looks like 6. So if I multiply the 6 to 120 or to 23, I get 138. So I write that underneath, I subtract down, and that number at the end is like my remainder, right? So you might have gone ahead and written your answer then as 6 plus 1 over 23, where this number 6, this is called the quotient, and the 1 is called the remainder. So like 6 divided, or 139 divided by 23 is like 6 and 1/23, or like 6 remainder 1. You guys kind of remember doing this back in elementary school or middle school. Should have been drilled the heck out of it. Guess what we're going to do with this? We're not going to be dividing numbers. Instead, we're going to be dividing polynomials. So we're going to be doing polynomial division. And there's 2 different types that we're going to talk about today. We're going to talk about long division first. So let's say that we have the division problem like this. So 2x cubed minus 4x squared plus 5x plus 1 divided by x squared minus 3. And we know that a fraction is the same thing as division, right? So we're cool with either way of writing it there, using like the little division bar. So we'll set it up the same way. So the divisor is going to go on the outside. And the dividend is going to go underneath. And I'm going to start by asking, how many times does x squared go into 2x cubed? So how many times does x squared go into 2x cubed? Okay, let me ask it a different way, since that seems, I'm going to ask, what times x squared gives me 2x cubed? So what times x squared gives me 2x cubed? Okay, so 2 times x squared will give me 2x squared. That's good. So the 2's are now the same, but the variable part isn't, right? 1 is x squared, 1 is x cubed. So let's make that 2x, right? So if I multiply 2x times x squared, I'm going to get 2x cubed. And then the negative 3, the non-leading or non-first term is just kind of along for the ride. So negative 3 times 2x is negative 6x. And then I'm going to subtract down. The number 1 place where students are going to make mistake is with the subtracting piece, because they're going to fail to distribute the negative. So I always start by doing this, and then I'm going to distribute the negative through. So that positive 2x cubed is going to become negative, and then the negative 6x is going to become a positive. And now I'm going to just compute straight down. So I have 2x cubed plus a negative 2x cubed. That's 0. Negative 4x squared plus 6x. What do you notice about that? Are those like terms? No. Is there something in the dividend that is a like term with the 6x? In the 5x over here, that's kind of annoying that they didn't line up, right? What if we, instead of starting it the way that we did, where we notice that that isn't lining up, I notice over here when I look at my divisor, I go from x squareds to constants. What did we miss in the middle? Like the linear term, just the x term? What if I just put in like 0x there as like a little placeholder? and we start the same way. And then it'll distribute the negative. And now when I add down, I get 0, I get negative 4x, I get 11x, negative 4x squared, and then I get 1 to come down. Now everything lines up nice, right? So my observation here is it's going to be helpful to include those missing terms, right? Like I want to put those, if I go from like x squareds to constants, anywhere in any of these polynomials, I want to include like a 0 and then whatever that missing degree is. That'll help keep everything nice and lined up for me so I don't accidentally do something silly like try to add 4x squared to 6x. You guys cool with that? Okay. So now I'm going to continue on. I'm going to ask what times x squared gives me negative 4x squared? What times x squared gives me negative 4x squared? Negative 4 is correct. Again, then I just multiply that to everything in my divisor. And then we'll subtract down. Again, I always distribute the negative. So that becomes a positive. That becomes a negative. And that becomes a negative. So when I add down, I have negative 4x squared plus 4x squared is 0. 11x plus negative 0x is still 11x. 1 plus negative 12 is negative 11. So that's like my remainder. But the way we're going to write this instead is, so we'd say the answer to this problem that we had at the start, which was this, is equal to my quotient plus my remainder over my divisor. Do you guys remember doing this last year in Algebra 2? Maybe you do, maybe you didn't. I think you probably did do this. But you probably did more of the other version. What's a nice piece is that there's a theorem that kind of predicts what that remainder is going to be. It's called the remainder theorem. It just says if I have some polynomial f of x, and I divide it by the polynomial x minus k, so some polynomial where the degree is 1 and the leading coefficient is 1, those type of polynomials are called monic polynomials. But if I divide f of x by a monic polynomial, the remainder is just going to be the same thing as if I plugged k into f. So for example, if I have f of x equals this guy, and I have a divisor x minus 2, and I want to find like the remainder, well, I could do the following. Is I can take that value for k and plug it in here. Or I could do it as a long division problem. Notice that we got the same result either way, right? Which of these would you rather do? The substitution seems a lot simpler and faster than doing the polynomial division, right? We're going to build off that idea in a moment. But before we do that, there's another theorem that's worth pointing out. Oops. This is called the factor theorem. It says that if a polynomial function f of x has a factor x minus k, if and only if f of k is equal to 0, i.e. it has a 0 remainder, right? Which should make sense, right? If I say, is 2 a factor of 4? You'd say yes, because 2 divided by 4 is 2, right? There's no remainder to that division problem. The same idea here. The beautiful part is, because of that remainder theorem, instead of actually doing the polynomial division to see if something's a factor, I can just do that substitution, which is nice, right? So is x plus 3 a factor of x cubed, or 6x cubed plus 25x squared plus 16x minus 15? Well, one way we could do that would be to do the polynomial division. So I'd say, okay, how many, or what times x gives me 6x cubed. Well, that would be 6x squared. And then when I subtract down, and then I'd say, okay, well, what times x gives me 7x squared? Okay, well, that's 7x. I multiply that over, and then I subtract down. And I ask myself, what times x gives me negative 5x? Well, that's negative 5. And I subtract down, I get remainder 0. So I'd answer yes, or instead, I could observe that this is a k equals negative 3. And I can just plug in negative 3 to this. So I'm going to have negative 27 times 9, or times 6. It's going to be negative 162 plus 9 times 25. That's going to be 225. And then 16 times negative 3 is negative 48. And then minus 15. And that all ends up to be 0. So I could answer yes that way also, right? Again, which one do you prefer? Well, just making a substitution is a heck of a lot simpler there, right? Now, I should say since x plus 3 is a factor of 6x cubed plus 25x squared plus 16x minus 15, we can say 6x cubed plus 25x squared plus 16x minus 15 is going to equal x plus 3 times some other polynomial, right? Now, doing the long division, I get that polynomial. But what don't I get if I did this method? I don't get that other piece, right? I'm not going to get that other piece and figure out how that thing factors, or how a partial factorization. What would be nice is to be able to split the difference. Could I do something that's quick and efficient, like just doing a substitution, but I still end up getting that polynomial somehow, so that I can write a partial factorization after doing my division? That's what we'd really want. Everybody agree with that? So the long division gives us stuff that substitution can't, but it takes a lot more work to get that information. Substitution gives us some of the information, and it's fast, but it doesn't give us that other factor. What we want is, or what we're going to show you next, is something called synthetic division. This is kind of the best of both worlds, but there is one catch. This only will work if our divisor is a monic polynomial, has degree 1 and leading coefficient 1. So you can't use this for all polynomial division problems. Specifically, if we went back and looked at this very first one, I couldn't use synthetic division because the degree here is 2, right? So I couldn't do synthetic division there. I'm stuck with what I had before, but I could do polynomial division here. And for the most part, with what we're going to be doing in this chapter, synthetic division will do me just fine. So almost always, for what we're going to be doing, this is going to work. So let's do an example of how to kind of get this and set this up. So let's go back to this same problem we just looked at that we did using long division. We did doing substitution, and show you what synthetic division looks like. Okay, so to start my synthetic division problem, I take the divisor and I set it equal to 0 and solve. So I get -3 when I do that. Everybody cool there? Okay. I'm going to take that and put it there. So I'm going to draw this little grid. And then I'm going to take the coefficients, just the coefficients from my dividend and put them there. So far, so good. I'm going to bring the first number down underneath the bar. That just happens for free. And then I'm going to take that number on the outside, multiply it by that first number underneath, write the answer in the next spot, and then add down. And I'm going to repeat that until I filled all of my spaces. So now I'm going to do -3 times 7. That's -21. I write that there, and then I add down. That gives me -5. And then I'm going to do -3 times -5. That's +15. I'll write that there and add down. And I'm out of spots, right? So I'm finished. These numbers at the bottom of this are now going to tell me about the result of this division problem. So if I start on the far right, that number is your remainder. The next number is the constant term, i.e. the degree 0 term. The next is the linear coefficient, i.e. the degree 1 term. The next one would be the quadratic coefficient, i.e. the degree 2 term, and you just kind of keep moving up 1 degree each time. So what this synthetic division tells us is that 6x cubed plus 25x squared plus 16x minus 15 divided by x plus 3 is going to equal this quotient plus this remainder over the divisor So this synthetic division process is kind of the best of both worlds, right? It's faster than long division, right? I can basically do this with no calculator if my, mental math skills are reasonably good. Just like I could do for substitution. And I can get the quotient out of it as well as the remainder. This is awesome. This is like the best of both worlds. Now the catch was it doesn't work on every single problem, but it's going to work on so many of them that it's like still my good close buddy. Yes. So let's continue and do some more examples of like illustrating what I can do with this. Oh, shoot. So it says here to use synthetic division and the remainder theorem to evaluate f of -5. So I remember that this is the same as the remainder for f of x divided by x minus -5. So I'm just going to do set up my synthetic division to find the remainder. Ah! I made a mistake. Who sees it? Take a quick look. Lucy, what is it? Yes! Look at that. I go from x to the fourths to x squareds. So remember when that happened up on this long division problem? Where was it? This one right here. Now, notice that if you were careful, you might have caught that like, hey, those two needed to line up. It is unrecoverable doing synthetic division if you miss the zero. If you miss the zero, you will not notice. You will just get the problem wrong. So there does need to be a zero there for the missing x cubes. It's like this isn't doing what I thought it was going to do. It's negative. So again, if I just do the synthetic division, that remainder at the end is going to be the same as the substitution, which is probably preferable because I don't want to do -5 to the 4th times 4. Like, that's a lot of maybe arithmetic that I'm incapable of doing in my head, as opposed to just like whole number multiplication, addition, subtraction. Like, that's should be able to do that. Yes, sir. Absolutely. Now, ideally, what have we been talking before this point? We've been talking about factoring polynomials, right? If we go back and we looked at our factor tree, let me just grab that, and I'm going to copy that in real quick. There are some missing pieces, right? Like if I had something that was 3 terms but not in the quadratic form, I didn't have anything I could do with this. If I had something with 4 terms and I couldn't factor it by grouping, I didn't have anywhere else to go. Sure. If I had 5 or more terms, there's nothing for me to do with this. What we want to do now is use what we've just uncovered to help complete this factoring tree, that if these polynomials are factorable over the real numbers, that we can find those factors. That we can complete more of those kinds of factoring problems. So that's going to be our goal now, is to build out and complete some of the uncompleted parts of this factoring algorithm. Is everybody cool with this plan? That's our goal. So the foundation of our plan here is going to be this factor remainder theorem, right? That if I can just check, if I get remainder 0, I know I found a factor. Everybody's cool with that plan? The question is, what k's do I want to check? Right? That's the first thing, because there's like infinitely many numbers I could be plugging in. I don't want to have to check infinitely many things. I'd like to have a list of like what is possible or not possible. And let me just check the possible things. Well, that's our next theorem. So say we have some polynomial of the form, this form. The rational zeros theorem says that every possible 0 for this polynomial is going to be of the form p divided by q, where p is a factor of the constant term, and q is a factor of the leading coefficient. So what I can do then is if I have some polynomial, I can use this theorem to create a list of possible factors. Okay. So my constant term is 4, well, negative 4, I guess. And my leading coefficient is 3. So my factors, what are the numbers that are factors of 4? What are the numbers that divide 4 evenly? There's 6 of them. Can someone tell me one of them? 2, great. What else? 4, what else? 1, okay. And what are we forgetting that you can always do? If a positive divides it, the negative is also going to, right? So I'm just going to tack like a plus or minus onto each of those. Is everybody okay there? How about for 3? What are factors of 3? Plus or minus 1 and plus or minus 3, right? Everybody's okay there? So my possible rational zeros then are going to be every factor of the constant term divided by every factor of the leading coefficient. So I'd have like 1 over 1, negative 1 over 1, 2 over 1, negative 2 over 1, 4 over 1, negative 4 over 1. And then I'd have like 1 over 3, negative 1 over 3, 2 over 3, negative 2 over 3, 4 over 3, negative 4 over 3. Does everybody see what I've done there? Now, who thinks that's annoying to write all that out? Here's what I would say. I'm okay with you just writing it this way. So as long as we understand what that means. What do you guys think? Does that seem like a fair deal? It's a heck of a lot more compact to write it that way as long as we understand what we're saying there. Of course. So this is good, right? I've gone down from like infinitely many things that I might have to check for possible to find a factor down to what is that? That's 12, right? You guys see that? Now that's a heck of an improvement. Can I do any better than that? Well, when I was your age in the same class doing the same thing, there were some tricks that we had to weed this list down, but for the most part, we kind of just had to check. Now, we did have one good trick where we can check for a bound, where we might be able to check one division and be able to cross off like a bunch of values as being impossible. So this theorem says if f of x is a polynomial with leading coefficient, we divide by k using synthetic division. If k is greater than or equal to 0, and every number in the bottom line of our synthetic division problem is non-negative, meaning positive or 0, then k is an upper bound for all the real zeros of f. So let's say that I did that for 1, and I got this result. That would tell me that anything bigger than 1 can't possibly be a solution. So I could cross out like another 3 possibilities from my list. Now, is that the greatest thing in the world? No, because it doesn't actually tell me anything other than like what it can't be. But am I happy to like chop 4 numbers off my list for the price of 1? That's a pretty good deal still. It's a pretty good deal. Now, for the most part, for us, we can do even better than this. Now, there is another half to this theorem. It says if k is less than or equal to 0, so like a negative, and every number in the bottom line alternates between non-negative and non-positive, then k is a lower bound for all the real zeros of f. So again, if I catch one of these that alternates, I say, okay, everything less than that value, I can discard also, which again is a good deal if I can get it, right? Like I get multiple cross-offs for the price of 1. What I would really like is just to get a remainder 0. That's what I'm really hoping for. But if I get either all positives or alternating between positive and negative, that's pretty good too. That's something where it helps me toss out some more possibilities. So let's look at an example of using this little theorem here that we've just kind of discussed. And then we'll talk about what you guys can do with your graphing calculator that makes like this little theorem kind of redundant or much less valuable to you than it was to me in the same class. Yes. All right, it says, show that every real zero of the polynomial f of x lies within the interval -5 to 4. So I want to show that -5 is a lower bound, and then I want to show that +4 is an upper bound. So to do that, I want to show that I get the alternating values at the bottom of my synthetic division. And then for the upper bound, I want all non-negatives at the bottom of my synthetic division. Everybody cool with the plan? Okay, so all I got to do is a little synthetic division to show this. I don't actually have to find all of the zeros and be like, oh, look, -5 is smaller than all of them. That could be real stinky to do. And I notice here that I got my alternating signs. So that tells me that I have a lower bound. Do the same thing for +4. Uh, 212. And that's going to be 848. That's going to be 833. So again, just the synthetic division alone can show me that I found a, upper or lower bound. Now, do I know that's like, the least upper bound or the greatest lower bound? No. I mean, the actual smallest zero here could be like -1, way bigger than -5, but there's nothing less than -5. And the actual biggest zero could be like +1, way smaller than 4, but I know there's nothing bigger than 4. So it doesn't tell me like, how like the tightest possible range there, but it does give me something, right? Can help narrow my search a little bit. Now, in practice, this, other than answering a question like we just did, is not something you would really readily use, because we can do an even better job than that with our graphing calculator. So let's say we're tasked to find all the real zeros for this polynomial. Observe quite quickly here before we get going. Could you factor this by grouping? I would say definitely not, because do you see two things that are, like, is there a factor between 83x and -30? Just a -1 or whatever, but it's not going to match the non-factor over here. So like, you couldn't factor this by grouping, right? There's no way using the factoring algorithm that we had built so far to deal with this. So we're going to start by finding the possible rational zeros. So that's going to be the factors of 30 divided by the factors of 6. So my factors of 30, 5, 6, 10, 15, 30, divided by factors of 6. Everybody's okay with this? Okay. So what I'm going to do now, these are all the candidates that I would like to do synthetic division with. I wouldn't go and check these blindly. Instead, what I'm going to do is I'm going to graph this f of x in my calculator. It's 83x. Oops, I forgot the squared there too. Great googly moogly. Here we go. So I'm going to get that in there. And then I'm just going to graph this on a normal-ish sized window. And what I'm looking for are x-intercepts. So that's places where the graph crosses the x-axis. If you remember from last lesson, the maximum number of x-intercepts or zeros this function can have is the degree, right? Do I see 3 of them? I see 1, I see 2, I see 3. So I know that I'm looking at them all, right? This one appears to be at -1, 2, 3, 4, 5, -6. Do that. This one looks like somewhere between -1 and 0. So that could be like 1/2 or 1/3 or 1/6 or 2/3 or 3 or 5/6. We're not really sure. Don't love that one. And the other one looks like somewhere between 2 and 3, right? You guys see that? again, a lot of possibilities there, right? You know, we could be like, like 5/2 or 5/3 or 10/6 or 15/6. Like there's lots of, unfortunately, there's like a lot of stuff there that are fractions. So the other thing I'm going to look now, if we go back to the previous lesson, we talk about that? Yeah, here it was. Is we're going to look at how the graph is crossing the x-axis. And I'm going to look to see if I have any bounces or bends going on my picture to see if any of these zeros might be used more than once. They all look like straight going through to me. Everybody agree with that? So only one time am I going to use them. I'll put like S's in top of all of these for straights. Of these, which one do you suppose is the one I would want to start my synthetic division with? The one that it looks like I'm pretty sure that that's got to be the x-intercept by looking at the graph. So let's start with that one. Again, I'm going to be careful and check to make sure there's no missing terms. We've made that mistake before. We don't want to make it again. So we got that remainder 0 that we're looking for. Woo, doggy! So what this is going to say for us then is 6x cubed plus 23x squared minus 83x minus 30 is going to equal x plus 6 times, again, remember this is the constant, the x coefficient, and the x squared, 6x squared minus 13x minus 5. Does that feel okay? So if I want to factor this completely, I know this piece is done because that's monic. You can't factor anything better than a monic. This piece, though, that's quadratic. That might still factor some more. Guess what? It's quadratic. So I'm just going to apply go back to my factoring algorithm, my factoring tree, and do it that way. Particularly since when I looked at the picture, there was a lot of possibilities of like what that number between 0 and 1 or between 2 and 3 could have been. Like I don't have just one choice. And if I have my options, do I want to do synthetic division with a fraction? I'd prefer not, right? That doesn't sound like a lot of fun. So instead, I'm going to go back to my factoring algorithm. So I'm going to say, okay, I want to find the two numbers that multiply to give me the leading coefficient times the constant term, and then add to give me that middle term. What are those two numbers that multiply to give me, negative 30, and then add to give me negative 13. Who sees the two numbers? Always do the multiplication part first. What are the things that multiply to give us negative 30? So I have negative 1 and negative 1 and 30, and then 1 and negative 30. Neither of those add to give me 13 though, right? Then I have negative 2 and positive 15, and then 2 and negative 15. There they are. So again, just start listing the factors, starting with 1 in the number, and eventually you'll find what you're looking for. Now remember, that doesn't take us straight to our result, right? All that does is tells us how to break up. Yes. Sure. Right? All it tells us is how to break up that middle term. We'll make two groups. Remember, that symbol in between the two groups always has to be a plus sign. So you might have to do, like, if it's subtraction, you have to write as plus a negative. From the first group, I can take out a 2x as a greatest common factor. From the second group, I can take out a negative 5 as a greatest common factor. If I look, both of these have a 3x plus 1 in common. After I factor that out, I'm left with a 2x minus 5. So if I go back up here, I can say this factors to 3x plus 1 times 2x minus 5. And there I'm done. Yes, sir. Sure. This is my primary tool that I'm going to be using, because now that I've factored this, if I'm looking for the real zeros, I can now just apply the zero product property, set each of these equal to 0, and solve. And those are my real solutions. This is where we're going to stop today. That was a whole heap of stuff that we just grinded through. You guys should be able to, though, now do up to 35. I think we have one more section in this chapter left to do, where we put the finishing or final finishing touches on this the synthetic division based factoring method. And then we're done with yet another chapter here. It's coming up quick. I think you're putting that on the wrong way. That's why I was being stubborn on you. Oh, it's the other cover? Oh, okay. That makes sense then.